Finally now, we're going to call back to spatial semantic pointers and continuous representations to build maps over continuous spaces. We know that VSAs can compose data structures. We've talked about lists and trees and graphs and rules, but what about a continuous space or structure like a trajectory, something that's moving through time over the world? Well, we can use SSPs to represent a continuous space as well. We can take a domain like XY, the Cartesian plane, and we can compose an SSP representation by fractionally binding the x-coordinate and then fractionally binding the y-coordinate with two different axis vectors, and then binding those two things together. What you see here on the right is a similarity plot between all the coordinates in this image encoded as SSPs, and a bundle of 2 points that are SSP values that we've placed here on the map. You can see that there's high similarity at these coordinates. We can use these SSPs as a basis for function approximation. And the experiment we're going to conduct next is using linear regression with SSPs to learn a function. We're going to do 2 experiments. We're going to look at what happens when we have a separable and a non-separable function and compare the binding versus the bundling coordinates together to create the representation. And what we'll see is how the choice of inductive bias affects our ability to learn functions and our stability in the face of reduced data sets.